Welcome back to Physics 142. We've been working on this complicated problem where we're using Kirchhoff's laws, this junction law and his loop law or loop rule to figure out what the current is in each of 5 different resistors in this complicated bridge circuit. So in the previous video, we were able to write down a bunch of equations that will help us here, all right? And specifically, we were able to use 2 different junctions, this junction here and this junction here, to write down 2 different junction equations, all right? That gave us independent information. All right, so we had 2 different junction equations, and then we drew 3 different loops, which gave us 3 more equations, so that's 5 total equations for our 5 unknowns. And I went ahead and I already substituted in for I4, this I1 minus I3, and for I5, this I2 plus I3. And so now we have 3 equations with 3 unknowns, right? I1, I2, and I3 are all unknown, and we have 3 different equations, and we need a way to solve this. Now, one approach to solving this would be to try to use substitution, right? So there, what you want to do is you want to try to get rid of variables. So maybe you would take this last equation here and solve it for something, like maybe you would take, or maybe this first equation, and maybe you take this first equation and you solve it for I3, right? And then you could substitute in for I3 here and I3 here, and then you would just have 2 equations that just have, you would have gotten rid of all of the I3s and you would just have I1s and I2s left, right? And so then you would solve one of them for either I1 or I2, substitute it in. I have to tell you that using this system of equations and using substitution, I worked it out. It is very nasty. To work it through all the way to the end. So in this video, I want to talk about 2 other approaches that you might take to solving a system of equations besides just using substitution. All right. And the first way that I wanted to talk about doing it is using matrices, all right? Your calculators all have a lot of powerful matrix tools, and you've probably encountered this in a math class somewhere, but I thought it would be useful to sort of just remember how you might take this system of 3 equations with 3 unknowns and solve it using matrix equations. So the first thing we need to do to solve this system using matrix equations is we want to get all of the I1s in a column, all of the I2s in a column, and all of the I3s in a column, right? Our 3 unknowns, I1, I2, and I3, we want to sort of organize these equations so that we have them in nice columns, all right? So I'm going to do that here. So for this first equation, I'm also going to start plugging in some of the values here, right? That I can plug in, like for I1, I could plug in, or sorry, for R1, I can plug in 150, right? And for R4, I can plug in 300, right? So maybe let's go ahead and actually just do that a second here. So if I take and I plug in all of these resistor numbers, I think I get a set of equations that look sort of like follows. 24 volts minus 150 I1 minus 300 times I1 minus I3 equals 0. So that's going to be the first equation with these resistances plugged in. The second equation with resistances plugged in is going to be 24 minus 50 times I2 minus 250 times I2 plus I3, and that will equal 0. And then this last equation looks like it's going to be minus 150 I1 minus 100 I3 plus 50 I2, all right? And now, like I was saying, we want to organize this in a way where we have all of our I1s together, all of our I2s together, and all of our I3s together. So what do I mean by that? Well, let's look at this. So if I combine the 2 I1s here, right, minus 300I1 and minus 150I1, I'm going to get minus 450I1, all right, plus 0 I2s in this equation, right? There are no I2s in this equation, plus 300 I3s, right? There's 300 I3s, right? The minus 300 and this minus side cancels, so it becomes a plus 300, all right? And then I'm going to take the 24, that constant, and move it over to the other side. So this is going to equal minus 24, all right? Okay, for the second equation, well, there's no I1s, so that's 0 I1 in the second equation, all right? And then the I2s, I have minus 250, minus 50 more, so that's minus 300 I2s, all right? And then I3, it looks like I have minus 250, minus 250 I3s, all right? And that, again, I'm going to move the 24 to the other side, so that gives us minus 24, all right? And then lastly, I have minus 150 I1, and then just I need to swap the order of the I2 and the I3, right? So plus 50 I2s, all right, and minus 100 I3s, and that all equals 0. All right, so now I've arranged this in a way that will allow me to write this as a matrix equation. All right, and specifically, you might remember that the way matrices work are you take rows of matrices and multiply them. You take rows and multiply by columns, right? And so how this ends up working is you can take all of the coefficients now that we've arranged this in columns with I1s, I2s, and I3s, you can take all of the coefficients and write them as sort of like a coefficient matrix. And so that's going to look something like this. All right, so now we're going to go over here, right, and write this as a matrix. And what that will look like is we'll have minus 450, 0, 300, and then we have 0, minus 300, minus 250, and then we have minus 150, 50, and minus 100. And that if we took all of those values and we multiplied them times sort of a vector here, I1, I2, I3, right? If we did matrix multiplication here, so that would be taking this row and multiplying it by this column, right? And then this row and multiplying it by this column, and then this row and multiplying it by this column, right? That would give us these equations back, except we also need what's on the other side, right? What would that end up equaling? Well, it would end up equaling minus 24, minus 24, and 0, all right? So this is taking these equations. Now I can write them as this matrix equation, all right? And so what people normally do here is we could give these matrices names, right? We could call this matrix A, all right? We could call this matrix, usually this would get referred to as like it's the matrix of the variables, the thing you're trying to solve, so that often might get called matrix X because it's what you're trying to solve for. And then maybe we'll call this over here matrix B, all right? And so we have here that A times B, or sorry, A times X equals B, right? A times X equals B. And so in linear algebra, the way that we can solve this is that we can multiply both sides of this equation by the inverse matrix to A, because A times its inverse is just going to sort of cancel out. It'll give you your identity matrix. And over here, we'll end up with A inverse on this side as well. So if we multiply both sides by A inverse, what you get is that X, that X matrix, must be A inverse times B, all right? And hopefully you remember this from a math class somewhere when you did sort of an introduction to matrices, all right? But the way that we solve this is we take the inverse matrix to A, put it over here, and so we get X is A inverse times B. Now, A inverse is something that you can do on your calculator. I'll link some videos of people doing this on like a TI-84 or something like that, but you just go in the matrix function on your calculator and you can type in this matrix, and then you hit the inverse button. You type in this matrix, you load up this matrix, you hit the inverse button. So you can go ahead and actually calculate A inverse. And so I did that on my calculator. All right, and for this matrix, when you calculate A inverse, you end up with the following matrix. All right, so A inverse here, and maybe I'll write it in a different color. All right, so let's go ahead and write what this ends up looking like here. All right, so A inverse ends up being the following matrix. All right, so A inverse now. So we're calculating A inverse. It's a nasty looking one. It's minus 17 over 1305. I can't read my own handwriting. I think that's a 6. There we go. And minus 1 over 870 and 1 over 725. And then you have minus 1 over 2175 and minus 2 over 725 and minus 1 over 1450, minus 2 over 725, 1 over 290, and minus 3 over 725. All right, so nasty looking thing, but your calculator can do it. All right, so that's A inverse. All right, and then we need to do matrix multiplication of this inverse matrix times B, right, which is minus 24, and 0. And so you can do that with your calculator. You just type in A in the inverse button and then times B, and that will give you the vector x. And so if you do this A inverse times B, you get an answer that's a vector that looks like this, or a matrix that looks like this, that is specifically 0.042, 0.094, and minus 0.017. All right, and so these then end up being your 3 currents, your I1, your I2, and your I3, right? So I1 is 0.42 amps, 0.042 amps, there we go. I2 is 0.094 amps, and I3 is minus 0.017 amps. And what does this minus sign mean? Well, it just means that in the original picture that actually the current must be flowing this way, right? That we got the sign wrong, so the current actually flows the other way through I3. We could then also calculate I4 and I5 by going ahead and plugging them in to these equations right here. But this is a way of using matrices to solve this equation. There's one other way that we can solve this equation that I should just mention, all right, and that's using a process called Gaussian elimination or row reduction. And so let me take just a minute or two to talk about how that works, how Gaussian elimination and row reduction work, all right? Here's the matrix stuff. So if you want to do row reductions to solve these equations, then you want to go through the sort of same step of organizing all of your equations where you still have I1s in a column, I2s in a column, I3s in a column, and then any power supply potentials on the other side, all right? So you still want to organize your equations in this way. You even could go so far as to organize things in a matrix, and there are plenty of videos online, maybe I'll share one, where they just show writing the matrix out like this and actually doing it with full row reduction, where you try to get 1s along this column and 0s down in the corner. But what I want to show you is just that you can use this organization as sort of a trick to sort of get you at a point where you can use substitution from there. So let me just show you how that works here. All right. So the idea is once you, when you have linear equations like this, all right, you can always take these equations and add them together to get new equations. All right, so you can add equations together to get new equations. The other thing that you can do is you can take these equations and you can scale them by a constant, right? So, I could multiply one equation by 3 or by 20 or whatever, right? I can, as long as I do the same thing to every term, that's fine. I can do that, all right? And so if you're clever about the way that you scale equations and that you combine equations, you can make things easier for yourself. You can eliminate variables. So as an example, let's say I wanted to get rid of this variable I3, right? I want to, reduce this down so that I only have I1s and I2s left, which would make this easier to solve, right? So if I want to get rid of I3, well, one thing that I could do is I could take this last equation here, and I could multiply the whole equation times 3, right? If I multiplied that whole equation times 3, and then I added it to this top equation here, that would end up getting rid of I3, right? And so let's see how that would work, right? So if I multiply this whole equation by 3, I would have minus 150, right, times 3, minus 150 times 3 would be minus 450, right? And so then I'd have minus 450 I1s, minus 450 more I1s, right? So here we're doing 3 times row 3, right, plus row 1, all right? And that's going to give us a new row, and specifically give us minus 450 minus 450 more. That'll be minus 900 I1s, all right? On the I2s, I have 150 I2s plus 0 more I2s, so that would be 150 I2s, so plus 150 I2s, all right? And then here I have 0 plus minus 24, so that would just equal minus 24. All right, so now I have a new equation that just has 2 unknowns, all right? And let's suppose then I wanted another equation. I wanted to get rid of I3 in another equation yet. Well, maybe if instead I take and I multiply this bottom equation by 2.5, all right? So if instead I do, and actually I should make it minus 2.5, all right? If I multiply it by minus 2.5, so this was 3, so if I do minus 2.5 times row 3, and then add it to row 2, all right, so then if I try combining rows 2 and 3, all right, and I want to get rid of I3, well, how do I get rid of I3? I need to take this 100 and multiply it by minus 2.5. That should do the trick, right? Then I will get the following. I will get this will become a plus, and it'll be 375, so plus 375 I1s, all right? Minus 2.5 times 50 here is going to give me, I think, minus 425. Oh, well, so minus 2.5 times 50 is 75, minus 75, right? But then, or sorry, 2.5 be 125. Thank you. All right, so minus 125 minus 300 more is minus 425 I2s, all right? And then that again equals minus 24. Now I have 2 equations with 2 unknowns. I could go ahead and row reduce this another step by trying to combine a couple of these equations, but at this point, it's probably easiest to just use substitution, right? So maybe I could solve this top equation for I1, right? And I would get I1 equals 24 plus 150 I2 divided by 900, right? And so that would be moving the I1 over to this side, moving the 24 over to this side, and then dividing through by 900, right? That would give me I1. Then I could substitute this expression in here for I1, and I would get that so then I would get 375 times this whole expression times 24 plus 150 I2 divided by 900 minus what did I say? I think I had minus 425, 25 I2s equals minus 24. And so then I could go ahead and I could solve this for I2, and I would end up getting that I2 equals 0.094 amps, which is exactly what we got from the other method, from the matrix method, right? I then plug this back in here to get I1, and plug them both back, say, or plug it in here to solve for I3. So that is, again, using the idea of row reductions, is another way that you can simplify your equations to make the algebra a little bit easier for these problems.